they projected its disappearance. By this point, 3I Atlas should have receded beyond the sun, lost from view and memory. But it persisted. And in this defiance, a transformation occurred. Its radiance, its swiftness, its stillness. And now, on the 15th day of December in the year 2025, Earth and 3I Atlas will converge in a celestial arrangement unseen in recorded history. Every observatory is focused. Every transmission is scrutinized, for it may well perform an act for which no one is prepared. NASA labels it a benign, extraterrestrial traveler. But what if the reality is that it awaits something, or perhaps a specific moment? Remain with me, for by the conclusion of this narrative, you will grasp why some believe that moment will not merely redefine astronomy, but fundamentally alter us. The countdown is tangible, and it has already commenced. If this enigma has you on edge, as it does me, do not linger in the shadows. Offer a like and subscribe, because you will not want to miss what transpires next as this unfolds in real time. Share your location and the current time, and whether you believe we are receiving the complete truth regarding these world-altering discoveries in the comments section. And if you wish to support the growth of this community, distribute this video across X, Facebook, Reddit, or even within your private conversations. You are the reason we can continue to pursue stories of this nature. Thus, my sincere gratitude for your support. Part 1. The countdown initiates. Envision this. You are standing in your yard on a clear night in late October of 2025, gazing skyward. All appears ordinary, tranquil. Yet, somewhere out there, accelerating at a velocity exceeding any human-made construct, an entity from beyond our solar sphere is hurtling towards an engagement we did not arrange. NASA assures you there is no cause for alarm. The European Space Agency deems it routine. They proclaim that December 15th will be an unremarkable day. However, here is what remains absent from their official statements. Here is what keeps amateur astronomers awake, constantly refreshing their telescope feeds and reevaluating their calculations. Something about 3I Atlas defies predictable behavior. We have cataloged the passage of only 3 interstellar objects through our cosmic vicinity. The first was Oumuamua in 2017, that elongated entity whose acceleration could not be solely attributed to gravitational forces. Its nature continues to be a subject of scientific debate. The second was Borisov in 2019, which exhibited characteristics more akin to a conventional comet, yet still prompted questions regarding its origin and composition. Now we confront 3I Atlas, the third interstellar visitor, and it deviates from the established pattern. On the first day of July in the year 2025, the Atlas telescope located in Chile captured an anomaly in its survey imagery, a faint luminescence moving against the backdrop of stars. Within days, astronomers determined its trajectory and comprehended the nature of their observation. This celestial body was not gravitationally bound to our Sun. Its orbital path was hyperbolic, signifying its origin from an interstellar origin, and its eventual return to that domain. The data revealed a remarkable velocity, approximately 60 kilometers per second. Its eccentricity, measured between 6.14 and 6.20, far exceeded the threshold distinguishing objects within the solar system from interstellar wanderers. It was approaching rapidly and would depart with even greater velocity. NASA and ESA promptly disseminated the fundamental details. Perihelion, the closest point of approach to the Sun, was anticipated around October 30th at an estimated 1.36 to 1.4 astronomical units. This position lies within Earth's orbital path, closer than Mars, yet still at a considerable distance. Subsequently, 3I Atlas would arc outwards, making its closest pass to Earth in mid to late December, at an approximate distance of 1.8 astronomical units, equating to roughly 168 million kilometers. They asserted there was no cause for concern, merely another transient visitor. However, a murmur began to spread across astronomy forums, within amateur observer circles, and in the comment sections of online videos discussing the comet. Individuals started sharing observations that diverged from the official projections. One report claimed a measured offset in the object's position several arc minutes from its predicted location, according to JPL Horizons. Another observer presented photometric data indicating fluctuations in brightness inconsistent with standard models of cometary activity. A third noted the tail appeared to extend in an unexpected direction, as if influenced by forces not accounted for in the prevailing models. The pertinent question is whether these observations hold validity, or if they are the result of calibration inaccuracies, atmospheric distortions, or wishful thinking. Because if 3I Atlas is indeed deviating, even marginally from its projected course, then our understanding of its December flyby may be fundamentally flawed. And if these deviations are systematic, escalating over time, then the geometry of December 15th might diverge significantly from the official orbital predictions. Allow me to illustrate the celestial mechanics of December 15th. By that date, 3I Atlas will have completed its perihelion passage over 6 weeks prior. It will be receding from the Sun, but still relatively proximate to Earth. More critically, the alignment will be nearly perfect. A straight line drawn from the Sun through 3I Atlas will extend almost directly towards Earth. We will be positioned downstream, within whatever wake it generates. If 3I Atlas has developed a plasma tail, if it has been expelling gas and dust energized by its close solar proximity, then Earth will be directly within the trajectory of such material. At a distance of 1.6 to 1.8 astronomical units, while considerable, it remains close enough for certain phenomena to propagate. Radio waves would traverse this distance in approximately 8 to 9 minutes. Charged particles carried by the solar wind could drift across this gap within days to weeks. Even gravitational influences, though infinitesimally weak, would be theoretically detectable. Therefore, the unspoken question arises. What if December 15th is not insignificant? What if this alignment triggers an unforeseen event? I am not suggesting an impact, as 3I Atlas will not be remotely close enough for such an occurrence. I am alluding to something more subtle, an electromagnetic pulse, a surge of radio waves, a sudden alteration in its brightness, a malfunction in our satellites, an unusual aurora appearing at latitudes where such phenomena are not typically observed. Something subtle enough to be dismissed as coincidence, yet perplexing enough to provoke inquiry. The official narrative is unequivocal and confident. 3I Atlas presents no danger. Its trajectory is well understood. The object is merely a comet, albeit one originating from beyond our star system. December 15th will arrive and pass without incident. However, confidence and certainty are not interchangeable. And within the silent intervals between press releases and public pronouncements, doubt finds its space. Questions arise. The possibility emerges that we are on the verge of witnessing something unprecedented, without our even realizing it. Part 2. The object that refuses to adhere to the rules. The officially designated discovery date is July 1st, 2025, but the saga of 3I Atlas actually commenced earlier, considerably earlier. When researchers reviewed archival data from the Hubble Space Telescope, they uncovered something unexpected. The comet was already exhibiting activity, producing a visible atmosphere of gas and dust while still situated approximately 6.5 astronomical units from the Sun, a distance beyond Jupiter's orbit. Comets are not expected to behave in this manner. Conventional understanding posits that they remain inert and frozen until they approach the Sun closely enough for solar radiation to initiate the sublimation of their icy components. Yet, 3I Atlas was already active, expelling material while still within the frigid outer reaches of the solar system. This prediscovery activity offers a crucial insight. This object is anomalous. It may be composed of exceptionally volatile substances that sublimate at lower temperatures than those typical for comets, or it may possess an internal heat source unknown to us, or it might not be entirely natural in origin. These are the potential explanations, each carrying significant implications. Let us examine the pertinent numerical data. Observations from the Hubble Space Telescope have established parameters for the size of 3I Atlas. The nucleus, its solid core, is estimated to be between 0.444 kilometers and 5.6 kilometers in diameter. This represents a substantial margin of error. It could be a relatively small conglomeration of ice and rock, or something considerably larger. Its dimensions are significant as they influence the quantity of material the comet can eject, the strength of its gravitational pull, and the potential energy it may contain if an internal source of heat is present. The Gemini Observatory tracked 3I Atlas through its perihelion, corroborating the Atlas telescope's findings, the hyperbolic trajectory and extreme velocity. Furthermore, Gemini provided new data through polarimetry. When light reflects off a comet's coma, it becomes polarized in a manner dependent on the size and composition of the dust particles. 3I Atlas displayed an unusual characteristic: extreme negative polarization. This signature suggests the presence of dust grains with anomalous optical properties, or a composition dissimilar to any known comet from our solar system. Now we arrive at the aspect fueling considerable conjecture: the amateur observations. Citizen scientists, equipped with backyard telescopes and CCD cameras, meticulously track objects like 3I Atlas and disseminate their findings online. Commencing in October, some of these observers began reporting discrepancies. One contingent claimed to have measured the comet's coordinates of right ascension and declination, finding offsets of several arc minutes compared to the predicted ephemeris. Another presented brightness curves that did not correspond to the expected decline as the comet moved away from the Sun. A third observed variations in the tail's structure, seemingly indicative of accelerations not governed by gravity. This is where the situation becomes complex. While amateur observations are valuable, they are also susceptible to error. Atmospheric refraction can distort light and alter apparent positions. Calibration errors can compromise photometric measurements. Telescope tracking inaccuracies can produce false indications of motion. Therefore, when an observer reports an arc-minute offset, we must question its veracity versus potential noise. The official ephemeris from JPL Horizons incorporates intervals of uncertainty. Minor deviations are anticipated and are considered normal. However, what if these deviations are not minor? What if they are systematic and progressively increasing? Let us perform a calculation. An arc minute at a distance of 1.8 astronomical units corresponds to a lateral displacement of approximately 780 kilometers. This is not insignificant. If 3I Atlas is indeed 780 kilometers off its predicted course, it signifies a substantial, unmodeled acceleration. Over a period of weeks, a minuscule, constant acceleration could accumulate to precisely this magnitude of displacement. What could be the cause of such acceleration? The most plausible explanation is asymmetric outgassing. When ice vaporizes on one side of the comet's nucleus, it generates a jet that propels the nucleus in the opposing direction. This is a recognized phenomenon observed in numerous comets, but the magnitude is key. For 3I Atlas to deviate by hundreds of kilometers, the outgassing would need to be exceptionally strong or remarkably one-sided. In such a scenario, the comet would be more active, more volatile, and more unpredictable than the models assumed. Alternatively, another possibility exists. What if these deviations are not attributable to outgassing at all? What if another factor is at play? A plasma interaction with the solar wind, a gravitational influence from an undetected mass, or even a propulsion system? Yes, I uttered the word. The concept may sound preposterous, but Oumuamua demonstrated that unconventional ideas sometimes warrant serious consideration. When an object behaves in a manner contrary to established physics, one faces two possibilities. Either our understanding of physics is incomplete, or the object is not what we perceive it to be. NASA's official stance remains unaltered. 3I Atlas is a comet. Its trajectory is comprehended. The approach to Earth in December poses no threat. However, here is what they are not disclosing. They are not providing daily updates on the object's position. They are not publishing detailed photometric analyses. They are not addressing the amateur observations that report anomalies. This reticence could signify nothing. It could indicate that their resources are allocated to other priorities. Or it could suggest they are awaiting resolution of the anomalies before issuing any public statements. December 15th approaches. Regardless of our readiness, the celestial alignment is fixed. Earth will be positioned with the Sun and 3I Atlas. We will be situated downstream of its tail, directly within the path of whatever it has been emitting since its perihelion. If the amateur observations are accurate, if the deviations are genuine, then the object might be closer than anticipated or oriented differently than predicted. In such a case, the alignment could be more precise, more significant than currently acknowledged. The central question is not whether an event will occur, but whether we will perceive it when it transpires. Part 3. The geometry of convergence. Visualize a clock. The Sun occupies the center, with the planets orbiting like hands sweeping across its face. Now imagine an interloper from beyond, a fragment of interstellar debris that disregards our predictable celestial clockwork, cutting across its face at an oblique angle, moving with a velocity far exceeding that bound by the Sun's gravitational pull. Such is 3I Atlas. And on December 15th, 2025, the hands of this cosmic clock will align in precisely the configuration required for an unusual occurrence. Let me clarify the geometric arrangement. Perihelion took place around October 30th, when 3I Atlas achieved its closest proximity to the Sun at approximately 1.36 astronomical units, roughly 204 million kilometers. This distance was sufficient for solar radiation to intensely heat the nucleus, vaporizing ices, releasing gases, and thus forming the coma and tail that render comets visible. For several weeks following perihelion, the comet has been progressing outward, ascending the gravitational gradient, and heading towards its eventual departure from the solar system. By December 15th, 3I Atlas will be situated at approximately 1.6 to 1.8 astronomical units from both the Sun and Earth. However, distance is not the sole determinant. Alignment is paramount. On that date, if one were to trace a straight line from the Sun through the comet, it would point almost directly towards Earth. We are not merely in proximity, we are downstream. We are within the anticipated zone of the comet's tail. Comet tails manifest in two primary forms. Dust tails consist of microscopic particles expelled outward by solar radiation pressure. They exhibit a gentle curvature, following the comet's orbital path. Ion tails are composed of charged particles, ionized by ultraviolet radiation from the Sun, and they point directly away from the Sun, propelled by the solar wind. If 3I Atlas possesses an active ion tail, and if that tail is appropriately oriented, then on December 15th, Earth will traverse through it. While 1.6 astronomical units might seem like a substantial expanse, it is. That equates to approximately 240 million kilometers. However, consider the phenomena capable of propagating across such a distance. Radio waves travel at the speed of light, covering the gap in roughly 13 minutes. Charged particles within the solar wind move at several hundred kilometers per second, requiring days to weeks to drift from the comet to Earth. Even relatively slow-moving dust particles, if sufficiently small and electrically charged, can be transported by electromagnetic forces. The pertinent question is not whether any substance from 3I Atlas can reach us, but rather what will reach us and what effect it will have upon arrival. Let us discuss coupling, a physics term describing the interaction and energy exchange between two systems. Earth possesses a magnetosphere, a protective field of magnetic energy shielding us from the majority of charged particle radiation emanating from the Sun. When this radiation impinges upon the magnetosphere, it can induce disturbances. Magnetic field lines reconnect, electric currents flow within the upper atmosphere, resulting in auroras and geomagnetic storms that can disrupt satellites and power grids. Now imagine that instead of the conventional solar wind, the magnetosphere encounters a stream of ionized particles originating from a comet's tail. Would the interaction differ? Would the coupling be more intense or less so? Would we observe phenomena that deviate from established patterns? The distances involved are considerable. At one point, 6 astronomical units, the density of the solar wind is significantly diminished compared to its intensity nearer Earth. The magnetic field carried by the solar wind is also weaker. However, a comet's ion tail can harbor its own magnetic structures, contorted loops and filaments formed by the interaction between the expelled gas and the interplanetary field. If Earth's magnetosphere were to encounter one of these structures, even briefly, it could instigate localized disturbances, auroras at unconventional latitudes, radio blackouts, or glitches in satellite telemetry. These effects would not be catastrophic, nor would they typically warrant headline attention, but they would be noticeable and would provoke questions. An additional possibility exists. What if the alignment transcends mere geometry? What if it pertains to timing? Suppose that 3I Atlas's passage through perihelion initiated an event, a release of stored energy, a surge of activity, or a transformation in the object's behavior. And suppose that event produced something that propagates outward at a specific velocity, precisely timed to reach Earth's location on December 15th. I readily concede that this is pure speculation, yet it is speculation grounded in physics. If an object emits electromagnetic radiation, it travels at the speed of light. If it expels particles, they travel at whatever velocity they are imparted. If it generates a disturbance in the interplanetary medium, that disturbance propagates as a wave. The timing could be coincidental, or it could be intentional. This is the point at which mainstream scientists typically express skepticism and disengage. They will assert that no mechanism exists for a comet to produce a directed effect. They will contend that any energy release would be isotropic, dispersing in all directions, rather than focused on Earth. They will argue that the alignment is inconsequential, a purely geometric coincidence that humans are imbuing with significance through pattern recognition. And they are likely correct. Probably. However, here lies the unsettling aspect. We have never before witnessed an interstellar comet traverse our solar system during the era of modern astronomy. Oumuamua was the first, yet it lacked a visible tail. Borisov was the second, but its orbital geometry differed. 3I Atlas presents a scenario for which we have no precedent. An interstellar visitor exhibiting an active coma and tail, approaching sufficiently close to interact with Earth's magnetosphere, and aligned in such a manner as to place us directly within its outflow path. We possess models and predictions, certainly, but models are only as reliable as the data upon which they are constructed. And we lack empirical data for this specific circumstance. December 15th represents a test, not one we designed or desired, but a test nonetheless. If nothing transpires, the models are validated, and the skeptics are vindicated. If something occurs, even something minor, we will learn that our understanding of cometary interactions was incomplete. In either scenario, we gain knowledge. However, I cannot help but ponder which outcome would be more disquieting: the affirmation that we comprehend all, or the revelation that we have been overlooking something all along. Part 4. 5 scenarios that nobody wishes to contemplate. I will now outline 5 hypotheses. 5 scenarios that could, in principle, produce observable effects on December 15th. I wish to state unequivocally from the outset that none of these represent mainstream scientific predictions. These are thought experiments. They are the types of ideas discussed in hushed tones following conference sessions or debated in late-night forum threads by individuals who relish pushing intellectual boundaries. Yet, they merit examination, because even the most speculative hypothesis can illuminate what is possible and what is not. Scenario 1. The silent activation event. The premise is as follows. The celestial body known as 3 Atlas has traversed the vast emptiness of interstellar space for countless millennia, remaining in a state of frigid inactivity. Its journey unexpectedly brought it into our solar system, drawing closer to the Sun, and for the very first time in its immense history, it began to warm. This thermal stimulus initiated a change within. Perhaps it was a molecular transformation deep within its core. Or possibly, it involved the vaporization of a volatile substance that, while stable in the void between stars, proved unstable under solar radiation. It might even be something far more peculiar, a latent energy reservoir, for which we currently lack a designation. Regardless of its exact nature, this process activated a perihelion encounter. The subsequent activation yielded an observable output, a surge of electromagnetic energy, an expulsion of particles, manifesting either as a focused beam or a dispersing wave. Should the timing and orientation align perfectly, this outward phenomenon would reach Earth on December 15th. The nature of our observation would depend entirely on the output's characteristics. If it were radio waves, we would detect a fleeting signal, potentially at frequencies outside our usual monitoring range. If high-energy particles were emitted, our cosmic ray detectors and satellite radiation monitors would register an increase. In the event of an electromagnetic pulse, we might witness transient interruptions in communication networks or power grids. While none of these potential outcomes would be catastrophic, they would certainly be perceptible and defy conventional scientific explanation. The second scenario proposes gravitational and plasma resonance. This is a more subtle phenomenon. The hypothesis suggests that the celestial alignment on December 15th establishes a configuration rendering Earth's magnetosphere exceptionally susceptible to disturbances in the interplanetary medium. Imagine it akin to the resonant frequency of a musical instrument. Striking the correct note causes the entire structure to vibrate. Normally, Earth's magnetic field is robust and provides ample shielding. However, under specific circumstances, such as when the solar wind possesses a precise velocity and magnetic alignment, even a minor perturbation can trigger a significant reaction. Now let us consider the possibility that the ion tail of 3 Atlas carries its own magnetic structures, and that these structures interact with Earth's magnetic field in a manner that triggers this resonant point. The consequence would be an amplified geomagnetic response. Auroras might manifest at latitudes where they are not typically observed. Ground-based magnetometers would record unusual fluctuations. Satellites in certain orbital paths could experience increased atmospheric drag or electronic interference. Again, this scenario does not imply an apocalyptic event, but it would be sufficient to appear in scientific data, prompting researchers to ponder the cause. The third scenario involves fragmentation and a burst of outgassing. Comets are inherently fragile bodies, not solid celestial spheres, but rather agglomerations of ice and dust bound by weak gravitational forces and even weaker cohesive properties. Occasionally, they fracture, particularly after a close passage to the Sun, when thermal stresses induce cracks within their nuclei. If 3 Atlas were to fragment around its perihelion, the resultant pieces would continue their trajectories on slightly divergent paths. Some of these fragments might expel gases and dust more intensely than the primary nucleus, creating temporary enhancements in the coma. If one of these outgassing events coincided precisely with the geometric alignment on December 15th, Earth could pass through a denser than anticipated cloud of cometary debris. Satellites in low Earth orbit would likely experience elevated atmospheric drag. An increase in meteor observations might occur as dust particles incinerate in the upper atmosphere. Optical telescopes could potentially detect a sudden surge in brightness or a modification in the tail's structure. This phenomenon would be short-lived, lasting perhaps hours, or at most, a few days. However, during that brief interval, 3 Atlas would exhibit behavior that contradicts existing models. The fourth scenario, the probe hypothesis, ventures into territory that most astronomers are hesitant to publicly acknowledge. Yet, as we are discussing possibilities, let us explore this further. Assume that 3 Atlas is not entirely a natural phenomenon. Conceivably, it harbors something artificial within its icy nucleus, a probe, a communication relay, or a dormant mechanism that has been drifting through space for eons, awaiting the opportune moment to activate. Its size need not be substantial. A device the dimensions of a car, embedded within a comet nucleus several kilometers across, would remain undetectable by our telescopes. Furthermore, it would not necessarily require continuous operation. Perhaps it awakens upon sensing the proximity of a star. It might harness solar radiation to replenish its power systems. Or it could wait until it assumes a specific geometric configuration, such as the alignment on December 15th, before transmitting a signal, a beacon, a data packet, directed towards a particular point in space. If Earth were to lie along this transmission path, we would receive the signal. This signal could be in radio frequencies, optical wavelengths, or an entirely different medium. It might be modulated in a manner that clearly distinguishes it from background noise, or it could be subtle enough to be detected only by specialized monitoring equipment. Researchers involved in the search for extraterrestrial intelligence, SETI, often contemplate such scenarios. A technological signature delivered directly to us by a wandering interstellar visitor. While it represents an extreme long shot, it is not physically impossible. The fifth scenario is the optical reflection phenomenon. This possibility is almost prosaic when contrasted with the others, yet it warrants mention. Imagine that on December 15th, the angular relationship between the Sun, 3 Atlas, and Earth reaches a specific point that maximizes the reflection of sunlight off the comet's coma. Consider it analogous to a glint of light off an airplane's fuselage at precisely the right angle, producing a brilliant flash. If the dust particles within the coma possess the appropriate size and composition and are arranged in a particular configuration, the comet could experience a sudden increase in brightness by several magnitudes for a duration of a few hours. Observers on Earth would witness a temporary elevation in luminosity. Social media platforms would likely be inundated with reports of an unusual celestial glow. Amateur astronomers would eagerly attempt to capture images, after which the phenomenon would subside, with the comet returning to its normal brightness as the geometric alignment shifted. This event would pose no danger, but it would be peculiar and unsettling, the kind of occurrence that fosters a sense of the universe conveying a message, even when it is merely physics manipulating light. These 5 scenarios encompass a spectrum from established physical principles to speculative conjecture. Their commonality lies in their technical feasibility. The probabilities associated with each vary significantly. Some are vanishingly improbable, while others are merely unlikely. Crucially, none of them contradict the known laws of nature. This very fact renders December 15th an intriguing date. It is not that we anticipate any of these scenarios occurring, but rather that we cannot definitively preclude them. In the space between expectation and certainty lies the potential for surprise. Part 5 delves into the architecture of institutional silence. NASA's official statement regarding 3 Atlas is concise and resolute. The object presents no threat to Earth, its trajectory is thoroughly understood, and the December approach is a standard occurrence that will be observed using established protocols. In essence, it conveys a message of normalcy and routine. Perhaps they are correct, and indeed there is nothing extraordinary to observe. However, a discernible pattern emerges in how information pertaining to 3 Atlas has been managed, a pattern that merits closer examination. Let us begin with foundational facts. When the object was first identified in 2017, it took several weeks for the scientific community to ascertain its interstellar origin. Initial observations suggested it was a typical asteroid. Only after meticulous orbital calculations did astronomers conclude they were observing something from beyond our solar system. The subsequent announcement generated immense public fascination, leading to widespread news coverage, documentary features, and even congressional inquiries. There was an insatiable curiosity regarding Oumuamua's identity and origin. With 3 Atlas, the process has diverged significantly. Its interstellar nature was recognized almost immediately. While the initial discovery announcement mentioned its hyperbolic orbit, subsequent information dissemination slowed to a mere trickle. There have been no major press conferences, no in-depth scientific publications in prominent journals, and no follow-up observations released to the public. The object is indeed being tracked, and data is undoubtedly being collected. But its dissemination lacks the transparency that characterized the communication surrounding Oumuamua. Why this discrepancy? One plausible explanation is that 3 Atlas is simply less scientifically compelling. It appears to be a comet, albeit one originating from another star system. Comets are common, and we have studied hundreds of them. Consequently, there may be little novel information to impart. However, this explanation fails to fully account for the observed anomalies. The prediscovery activity at considerable heliocentric distances is unusual. The extreme negative polarization is atypical. Reports from amateur observers regarding trajectory and brightness anomalies are also noteworthy. There is, in fact, ample scientific intrigue surrounding this object. So, why the reticence? Another possibility is a deliberate stance of caution. Space agencies learned from the Oumuamua incident that premature disclosure of surprising findings can incite a media frenzy that escalates uncontrollably. Recall how swiftly Oumuamua transitioned from an asteroid to a potential alien probe in the public consciousness. NASA may be intentionally downplaying 3 Atlas to circumvent a recurrence of such a spectacle. The preferred approach might be to await the completion of data analysis and the establishment of definitive interpretations before issuing any statements that could be misconstrued or sensationalized. However, a third, more disquieting possibility exists. What if the silence is not born of caution or disinterest, but rather of uncertainty? What if NASA and the European Space Agency, ESA, are encountering data that they do not comprehend and are reluctant to discuss until a satisfactory explanation emerges? Institutional science inherently embraces risk aversion. Announcing an anomaly prior to its elucidation can have detrimental career consequences. It is far more prudent to maintain silence, conduct further observations, meticulously re-verify calculations, and only then proceed with public disclosure once a complete narrative has been established. Now let us address the established protocols. The International Academy of Astronautics has formulated a set of guidelines known as the Post-Detection Communication Protocols, designed to manage situations involving potential technosignatures. These protocols delineate the procedural steps to be undertaken if a signal of potential extraterrestrial origin is detected. Key elements include rigorous verification, consultation with independent experts, and ultimately, public dissemination of information. However, a built-in delay mechanism is a central tenet. The protocols emphasize that no announcement should be made until the detection has been unequivocally confirmed and its implications fully understood. Has 3 Atlas triggered any of these protocols? We cannot be certain. The protocols are primarily intended for radio signals and deliberate transmissions, not for the ambiguous behavior exhibited by a comet-like object. Nevertheless, some observers have speculated that the distinctive characteristics of 3 Atlas may have prompted informal consultations among SETI researchers and planetary defense experts. If there exists even a remote probability that the object is artificial or carries some form of signal, such discussions would undoubtedly be occurring behind closed doors. The Planetary Defense Coordination Office, a division within NASA's Office of Planetary Defense, maintains a roster of celestial bodies requiring enhanced monitoring. This list includes near-Earth asteroids possessing indeterminate trajectories or unusual properties. While 3 Atlas does not technically qualify as a near-Earth object, as it is not gravitationally bound to our solar system, some online forum discussions have claimed its temporary inclusion on internal watch lists utilized for training exercises or protocol development. These assertions remain unverified, and NASA has neither confirmed nor denied them. However, if true, it would suggest that some entity within the scientific infrastructure deemed 3 Atlas worthy of additional scrutiny. This brings us to the realm of psychology. Humans are inherently inclined to seek patterns and discern connections, even in the absence of genuine correlation. When an institution withholds information, the resulting void is often filled with speculation. The absence of knowledge inadvertently becomes interpreted as evidence of concealment. This is the genesis of conspiracy theories, not necessarily from malice, but from the chasm between our desire for understanding and the information we are provided. December 15th has become a focal point in online discourse precisely because it represents a specific, tangible point in time. If one is inclined to believe that something unusual is transpiring with 3 Atlas, a temporal marker is essential. December 15th provides that marker. It is sufficiently proximate to feel imminent. It is specific enough to facilitate predictions and preparations, and it is aligned with enough celestial geometry to appear plausible. Whether any extraordinary event actually transpires on that date is almost secondary. The date itself has acquired significance through its repeated citation in various contexts. My intention is not to assert whether NASA is concealing information. I lack the capacity to know. However, I can state that the structure of institutional silence fosters an environment where doubt can flourish. Every unresolved question becomes a breeding ground for suspicion. Every delay in data release is perceived as potential evidence of a cover-up. And every assurance that there is no cause for alarm paradoxically reinforces the belief that something indeed warrants concern. This dynamic is unfolding in real time as December 15th draws nearer. The silence persists, the questions remain unanswered, and the countdown continues. Part 6 examines lessons learned from previous celestial visitors. In October 2017, a telescope at the University of Hawaii, engaged in scanning the skies for near-Earth asteroids, detected an object of unprecedented nature. Its velocity and orbital inclination were such that it could not possibly be gravitationally bound to our Sun. The discovery team christened it Oumuamua, a Hawaiian term signifying scout or messenger, a designation that would prove remarkably prescient. Oumuamua presented as unlike anything previously encountered. Its inferred shape was highly elongated, possibly 10 times its width. It displayed no signs of a coma or tail, thus deviating from the conventional definition of a comet. However, as telescopes tracked its progress over the subsequent weeks, a peculiar observation emerged. The object was accelerating. This acceleration, though minute, exceeded what gravitational pull from the Sun alone would dictate. This non-gravitational acceleration became the central enigma of Oumuamua. Scientists proposed a variety of explanations. One possibility was that it was outgassing after all, but so faintly that the coma remained invisible. Another hypothesis suggested radiation pressure, the momentum transfer from sunlight reflecting off its surface, was providing the additional impetus. Some even posited a combination of both. Yet none of these explanations perfectly reconciled with the observed data. The acceleration appeared too significant for radiation pressure, unless the object possessed an exceptionally low mass and thickness. The absence of a discernible coma made the outgassing hypothesis problematic. Consequently, debates ensued. Certain researchers, including Harvard astronomer Avi Loeb, suggested that Oumuamua might have an artificial origin, perhaps a light sail or a probe, something constructed rather than naturally formed. The broader scientific community largely dismissed this notion, adhering to the principle that extraordinary claims necessitate extraordinary evidence, and the evidence for Oumuamua's artificiality was considered insufficient. Nevertheless, this controversy imparted a valuable lesson. When an object behaves in ways that defy our expectations, we must remain open to considering unconventional explanations, not as an initial resort, but as viable possibilities that persist when conventional explanations falter. 2 years later, in August 2019, amateur astronomer Gennady Boris discovered a second interstellar visitor using a telescope he had constructed himself. This object was unequivocally a comet, exhibiting a luminous coma and a tail. Spectroscopic analysis of its composition indicated similarities to comets originating from our own solar system. In many respects, Borisov was precisely what had been anticipated for an interstellar comet, which was a source of reassurance. It suggested that Oumuamua might have been an anomaly, an unusual case, rather than an indication that our understanding of interstellar objects was fundamentally flawed. However, even Borisov presented its own surprises. Its ratio of carbon monoxide to water differed from that of typical solar system comets. Its nucleus fragmented as it approached the Sun, breaking into multiple pieces that dispersed along its orbital path. And, much like Oumuamua, it exhibited non-gravitational acceleration attributed to outgassing, though in Borisov's case, the mechanism was clear and uncontested. Now we have 3 Atlas, the third interstellar visitor. What insights does it offer? Firstly, it demonstrates the diversity of these objects. Oumuamua lacked a visible coma, while Borisov possessed a prominent one. 3 Atlas exhibits extreme polarization and unusual dust characteristics. Each object is distinct, challenging our assumptions in its own unique way. Secondly, non-gravitational accelerations appear to be a common trait among interstellar objects. Both Oumuamua and Borisov displayed them. If amateur observations suggesting that 3 Atlas is also deviating from its predicted path are accurate, this would mark 3 for 3. Thirdly, our capabilities for detection and characterization are continuously improving. We discovered Oumuamua only after it had passed perihelion and was exiting the solar system. We identified Borisov several months prior to its perihelion, affording us ample time for study. We detected 3 Atlas even earlier, with pre-discovery observations extending back to its distant approach from the Sun. This progressive advancement is significant. Each interstellar object we identify enhances our knowledge of the cosmos and our methods of studying it, while simultaneously revealing the vastness of our ignorance. Prior to 2017, our understanding of interstellar objects was theoretical, lacking direct observational evidence. Now, with 3 examples, each has posed as many questions as it has answered. How prevalent are objects like Oumuamua? From whence do they originate? How much time do they spend in interstellar space before encountering a stellar system? Do objects exist that are even more unusual than those we have observed thus far? The history of these 3 visitors also highlights recurring patterns in the responses of both the scientific community and the public. With Oumuamua, initial excitement gave way to intense scrutiny and subsequent controversy. With Borisov, there was interest but less drama, as it aligned more closely with expectations. With 3 Atlas, we are still in the nascent phase. Data is incomplete, and interpretations remain preliminary. However, the seeds of controversy are already being sown by amateur observations and trajectory anomalies. If December 15th passes without incident, 3 Atlas will likely join Borisov in the category of intriguing but not earth-shattering discoveries. Should something unexpected occur, even something minor, it could ascend to the status of Oumuamua, becoming a source of debate and speculation that endures for years. There is a fundamental lesson in all of this: humility. Each of these objects has served as a reminder that the universe is under no obligation to conform to our established models. We formulate theories based on the available data, but the data we possess is always incomplete. Interstellar objects traverse the void between stars for millions or billions of years, encountering environments and conditions that are exceedingly difficult to replicate in terrestrial laboratories. Upon entering our solar system, they carry information about processes and compositions that may be rare or absent in objects formed within our own system. The pertinent question is not whether 3 Atlas will surprise us, but rather whether we are prepared to be surprised. Do we possess the necessary instruments, funding, attention, and intellectual flexibility to recognize and comprehend something truly novel when it appears? Oumuamua eluded us before we could obtain a comprehensive observation. Borisov afforded us more time, yet still left unanswered questions. 3 Atlas remains within our observational reach, continuing its approach toward its point of closest alignment. We have been presented with an opportunity. Whether we utilize it wisely remains to be seen. Part 7 explores how amateur eyes perceive what professionals overlook. A quiet revolution is underway in the field of astronomy. It is not being spearheaded by multi-billion-dollar space observatories or governmental agencies, but rather by individuals equipped with backyard telescopes, modified digital cameras, and an unwavering passion for observing the night sky. These amateur astronomers, while lacking professional credentials or research grants, possess something equally valuable: time, dedication, and freedom from institutional constraints. When the announcement of Comet 32 Atlas was made in July of 2025, the community of amateur skywatchers responded with immediate enthusiasm. Within mere days, enthusiasts across the globe were actively observing the comet, meticulously noting its position, quantifying its luminosity, and capturing images of its ethereal coma and trailing tail. While some utilized cutting-edge scientific instruments, others relied on comparatively modest setups. Yet, a unifying characteristic bound them all: the open sharing of their gathered data through online forums and public databases, making it accessible to anyone interested. It was within this open exchange that the initial discrepancies began to surface. To clarify, let me elaborate on the fundamental principles of astronomical positional measurement. When you capture an image of a celestial body, you are effectively recording its location relative to the backdrop of fixed stars. By possessing the precise coordinates of these reference stars, one can then deduce the coordinates of the object under observation. This technique is known as astrometry. While seemingly straightforward, this process is inherently susceptible to numerous sources of error. Your telescope might not be perfectly calibrated or aligned. Atmospheric conditions can distort the path of light. The sensor of your camera could exhibit inherent imperfections. Any of these factors, individually or in combination, can introduce inaccuracies ranging from several arc seconds to even entire arc minutes. Professional observatories meticulously address these potential errors through rigorous calibration protocols. They employ extensive star catalogs, which contain positions measured with astonishing millisecond precision. Furthermore, they utilize sophisticated models, taking into account atmospheric temperature and pressure, to correct for light refraction. By averaging multiple independent observations, they effectively mitigate random noise. The outcome is a level of positional accuracy measured in fractions of an arcsecond. Amateur observers, as a general rule, cannot achieve this caliber of precision. Their typical margin of error is significantly larger, often falling within the range of 5 to 10 arcseconds. Therefore, when an amateur astronomer reports that 3 Atlas is displaced from its predicted location by several arc minutes, a critical question arises. Is this a genuine phenomenon or a consequence of observational error? An arc minute is equivalent to 60 arcseconds, which is 10 times the typical uncertainty for amateur measurements. Explaining an arc-minute displacement as a pure measurement error becomes a considerable challenge. Unless a significant flaw occurred in the observational procedure, it's equally difficult to attribute such a deviation to a real physical anomaly, unless the comet is experiencing exceptionally potent non-gravitational forces. This is where the situation becomes particularly intriguing. Numerous amateur astronomers, employing diverse equipment from disparate locations, have reported comparable positional offsets. While not identical, these discrepancies exhibit a discernible correlation. They consistently observe the comet shifted in a similar general direction when compared to the predictions provided by orbital ephemerides. This widespread agreement makes it significantly harder to dismiss the findings as mere random error. When independent measurements converge, even if individually they possess a degree of imprecision, it strongly suggests that they are capturing an actual physical reality. The pertinent question, then, is what exactly are they observing? One plausible explanation is that the ephemeris itself is inaccurate. The official predictions generated by JPL's horizon system are derived from orbital elements calculated using initial observational data, gathered when the comet was still at a considerable distance from the Sun. If these early measurements contained minor inaccuracies, or if the orbital computation failed to adequately account for non-gravitational accelerations, the predicted position could gradually diverge from the comet's true trajectory over time. By December, such accumulated errors could become substantial. An alternative hypothesis is that 3 Atlas is indeed undergoing non-gravitational accelerations that were not incorporated into the initial orbital solution. Comets are notoriously prone to such effects. As they approach the Sun, sublimation of their icy components generates jets of material, exerting unpredictable forces on the nucleus. While these effects are typically minor, they can accumulate significantly over extended periods. For a comet as demonstrably active as 3 Atlas appears to be, these accelerations could be substantial enough to induce noticeable deviations from its predicted path. Let us perform a simple calculation. Assume 3 Atlas experiences a non-gravitational acceleration of 10 to the power of -5 meters per second squared. This is an exceedingly small acceleration, roughly 1/millionth of Earth's surface gravity. Over the span of a single month, such an acceleration would alter the comet's velocity by approximately 26 meters per second. Extending this period over 2 months, from perihelion until December 15th, the velocity change would amount to 52 meters per second. This change in velocity directly translates into a positional offset. Employing basic kinematic equations, an acceleration of 10 to the power of -5 meters per second squared acting for 60 days would result in a displacement of approximately 1,500,000 kilometers. At the orbital distance of 33 Atlas, this vast linear displacement corresponds to an angular offset of roughly 5 arc-minutes. Consequently, a deviation on the scale of arc-minutes is indeed plausible if the comet is subjected to a moderate level of non-gravitational acceleration. The crucial question then becomes whether this acceleration is presently factored into the official orbital solution. If it is already accounted for, then the amateur observations are either flawed or indicative of phenomena beyond typical cometary behavior. If, however, it is not included, then JPL would need to update their ephemeris by incorporating more refined force models. Shifting our focus to photometry, this pertains to the measurement of an object's brightness. Amateur astronomers have been diligently tracking the luminosity of 3 Atlas since its discovery, and some of these observers contend that its light curve deviates from predictive models. Specifically, they report that the comet's brightness is diminishing at a slower rate than anticipated as it recedes from the Sun, or that it is exhibiting unexpected surges in brightness. The prediction of cometary brightness is an exceptionally challenging endeavor. It is contingent upon numerous factors, including the size of the cometary nucleus, the volume of dust and gas being released, the reflective properties of these particles, and the specific geometric configuration of the observation. Professional models typically rely on empirical formulas that have been calibrated using data from past cometary observations. However, each comet possesses unique characteristics. While some comets adhere closely to these established formulas, others exhibit marked departures. Therefore, a discrepancy between predicted and observed brightness is not necessarily a cause for alarm. It might simply indicate that this particular comet is displaying a level of activity that is either higher or lower than the average. Nevertheless, there is a subtle but significant nuance to consider. If these observed brightness variations are systematic, meaning they manifest in discernible patterns that correlate with the comet's position in its orbit or its orientation. This could signal the presence of something genuinely interesting. For instance, if the comet experiences a noticeable brightening whenever it assumes a specific orientation relative to Earth, this might suggest a directed outburst of material or the presence of a particularly reflective surface feature. Such intricate details are precisely the kind of information that can only be uncovered through meticulous and continuous monitoring by a broad network of observers. It is this diligent monitoring that the amateur astronomical community is actively undertaking. They are constructing light curves with a resolution that can be as fine as daily or even hourly. They are actively comparing their findings, cross-validating their measurements, and engaging in debates regarding their interpretations, all conducted openly on public forums and social media platforms, allowing for widespread public engagement. This transparency serves as both a significant strength and a potential vulnerability. It facilitates the rapid dissemination of information and fosters collaborative problem-solving. Conversely, it also allows for the swift propagation of errors and misunderstandings. Consequently, this is our current juncture. The collective observations from amateur astronomers point towards anomalies, including positional displacements, variations in brightness, and alterations in tail structure. Some of these might represent genuine phenomena, while others could be mere artifacts of the observational process. The paramount challenge lies in distinguishing genuine signals from inherent noise. Professional astronomers possess the necessary instrumentation and expertise to perform this crucial separation, yet they do not always actively engage with or adequately consider the reports from amateur observers. A perceptible chasm exists between these two communities, characterized by a disconnect in both communication and mutual trust. Amateur astronomers often feel their data is overlooked by professionals, while professionals in turn perceive amateurs as prematurely drawing conclusions without sufficient, rigorous calibration. The celestial alignment on December 15th presents an opportunity to bridge this divide. Should this alignment produce any observable effect, amateur astronomers will be diligently watching. They will meticulously record, measure, and disseminate their findings instantaneously. Conversely, if no discernible event occurs, they will document that outcome as well. Regardless of the outcome, their collective observations will undoubtedly become an integral part of the historical record of Comet Through 2 Atlas. And perhaps, just perhaps, they will succeed in detecting something that the professional scientific community might have overlooked. Part 8. The physics of the impossible. Let us delve into the realm of forces. Everything that traverses the cosmos is subject to pushes and pulls from various sources. Gravity is the most obvious and pervasive force, shaping the orbits of planets and comets around stars, and holding moons in their paths around planets. However, gravity is not the sole operative force in the universe. Radiation pressure, the momentum imparted by photons of light, exerts a subtle influence. The solar wind, a continuous stream of charged particles emanating from the sun, also plays a role. Furthermore, electromagnetic interactions, the complex interplay between magnetic fields and electric currents, contribute to the forces acting upon celestial objects. All these forces collectively influence the motion of comets, potentially causing deviations from purely gravitational trajectories. For the vast majority of comets, the most significant non-gravitational force stems from the rocket effect generated by outgassing. As ice on the sunward side of a comet's nucleus sublimes, it transforms into gas, which then expands outward with considerable velocity. This expanding gas carries momentum. If the nucleus is rotating, and if the outgassing is more intense on one side than another, the resulting imbalance in momentum creates a propulsive thrust. This phenomenon can be likened to a leaky balloon spinning erratically as it deflates. Although the effect is generally small in magnitude, over periods of weeks and months, it can accumulate to produce a significant change in the comet's motion. We can estimate the magnitude of this force. Consider a cometary nucleus with a radius of 1 kilometer and a density of 500 kilograms per cubic meter, equating to a total mass of approximately 2 trillion kilograms. If this nucleus is sublimating water ice at a rate of 1,000 kilograms per second, and the escaping gas has a velocity of 500 meters per second, the resulting thrust would be in the order of 500,000 newtons. Dividing this force by the total mass yields an acceleration of approximately 2.5 times 10 to the power of -7 meters per second squared. This is an incredibly minuscule acceleration, but it is nevertheless a non-zero value. Over a period of 60 days, such an acceleration would induce a velocity change of 1.3 meters per second, resulting in a positional displacement of about 34,000 kilometers. At the distance of 3 Atlas from Earth, this displacement of 34,000 kilometers translates to approximately 13 arc-seconds. This magnitude is measurable, but it falls within the range of noise typically encountered in amateur observations. To account for the arc-minute scale offsets reported by some observers, accelerations 10 to 20 times greater would be required. Such an amplification would necessitate either significantly more intense outgassing or the presence of an additional contributing force. Could the outgassing be this pronounced? It is a distinct possibility, especially if the comet is exhibiting an unusually high level of activity. Recall the pre-discovery data indicating activity at an astounding 6.5 astronomical units, a distance far beyond where water ice typically sublimates. For a comet to be active at such a remoteness, it would need to be exceptionally rich in more volatile ices, such as carbon monoxide or carbon dioxide. These substances sublimate at considerably lower temperatures, and their sublimation process can generate exceptionally strong outgassing. Another potential factor involves the comet's rotational state and its physical shape. If the comet's nucleus is rotating rapidly and possesses an irregular form, the outgassing process would likely be highly asymmetric, concentrated in specific regions, and directed in particular vectors. Should these directional thrusts consistently align in a manner perpendicular to the Sun-comet line, the resulting acceleration could dramatically alter the comet's trajectory in unforeseen ways. This very scenario bears a striking resemblance to what was observed with Oumuamua, where the non-gravitational acceleration could not be adequately explained by uniform outgassing alone, necessitating the inference of some form of asymmetry or preferred directional thrust. Now let us consider the influence of electromagnetic effects. Comets possess ion tails composed of charged particles. These particles interact with the interplanetary magnetic field, which is carried by the solar wind. This interaction can give rise to electric currents and generate magnetic forces. Could these forces be sufficiently potent to exert a noticeable push on the cometary nucleus? It is highly improbable. The mass of the ion tail is minuscule in comparison to the mass of the nucleus. Even if the ions themselves experience significant forces, the transfer of momentum back to the nucleus would be negligible. However, the ions themselves could be deflected, leading to the formation of tail structures that do not precisely point away from the sun. This deflection could, in turn, influence how we measure the center of light within the coma, potentially introducing apparent positional offsets. A more speculative possibility involves plasma interactions. The solar wind itself is a magnetized plasma, a complex mixture of charged particles permeated by magnetic field lines. As a comet's coma and tail traverse this plasma, they create disturbances, generating waves and instabilities. Under specific conditions, these instabilities can manifest as localized electric fields and electric currents. Could such fields exert an influence on the trajectory of the nucleus? While seemingly unlikely, it is not entirely outside the realm of possibility. If the nucleus were to accumulate a net electric charge, and if the surrounding plasma possessed a suitable structural configuration, a minor electric force could theoretically be generated. The precise magnitude of such a force would be entirely dependent on unknown factors, including the nucleus's charge, the strength of the electric field, and the plasma density. What about gravitational anomalies? Could there be an undiscovered mass in proximity to 3/4 Atlas that is subtly perturbing its orbit? Perhaps a small asteroid, or even a fragment originating from the nucleus itself. The magnitude of any such perturbation force would scale with the mass of the unseen object and inversely with the square of the distance. To produce effects significant enough to be observed, one would require either a substantial mass located very close by or a moderately sized mass situated at a relatively close distance. However, if another celestial object were in such proximity, it is highly probable that our current astronomical surveys would have already detected it. Our observational capabilities are adept at discovering such objects. Therefore, this particular explanation appears less convincing, unless the hypothetical object were exceptionally dark and small. Let us take a step back and consider the fundamental question we are attempting to address. We are endeavoring to explain why certain amateur astronomers report observing anomalies in both position and brightness. However, before invoking elaborate and exotic physics, it is prudent to first consider the more straightforward explanations. Perhaps these reported anomalies are not real. They might be the result of measurement errors, calibration inaccuracies, or simply wishful thinking. This represents the null hypothesis. The burden of proof undeniably rests upon those who claim the existence of anomalies, to provide compelling evidence that their observations are robust, reproducible, and free from systematic error. If, however, the anomalies are indeed confirmed to be real, then a plausible physical mechanism must be identified. Asymmetric outgassing stands out as the most likely candidate. This phenomenon is well documented, has been observed in numerous comets, and possesses the potential to generate the observed magnitude of deviation. Yet, if outgassing alone cannot fully account for the observed phenomena, we are then compelled to explore less conventional hypotheses. These might include plasma interactions, charge accumulation, or even fragmentation of the nucleus. Each successive step takes us further away from the comforting predictability of textbook physics and into the domain of educated conjecture. And if none of these conventional explanations prove adequate, if we exhaust all known physical mechanisms and still cannot reconcile the observations, then we find ourselves venturing into uncharted territory. It is at this juncture that scientists begin to formulate truly speculative hypotheses. This is the point where research papers are published with titles such as Anomalous Acceleration of Interstellar Object through Atlas, Implications for Composition and Activity. This is also when scientific conferences become exceptionally engaging. However, we have not yet reached that stage. We are still operating within the phase where the majority of scientists believe the observations are likely erroneous and the underlying physics remains within the bounds of the known. The events of December 15th are poised to serve as the ultimate test. If the predicted alignment yields a measurable phenomenon that cannot be readily dismissed as error or random noise, then the nature of the scientific discourse will undoubtedly shift. Until then, all remains speculative. Part N. Signals from the Silent Universe. In the year 1974, humanity undertook a significant endeavor, transmitting a message into the vast expanse of space. Using the Arecibo radio telescope situated in Puerto Rico, a deliberate sequence of binary digits was beamed towards the globular cluster Messier 13, located approximately 25,000 light-years away. This message was meticulously designed to encode fundamental information about humanity, encompassing details of our biochemistry, our physical appearance, and the structure of our solar system. The transmission was largely symbolic in nature. The signal itself is not expected to reach its intended destination for a staggering 25 millennia. Even under the most optimistic scenario, where a recipient intercepts the message immediately and responds without delay, it would take another 50,000 years for any reply to reach us. Nevertheless, the very act of sending this message held profound significance. It served as a declaration. We exist, we are intelligent, and we are actively listening. Our vigilance in listening has continued unabated ever since. The search for extraterrestrial intelligence, or SETI, has employed radio telescopes worldwide to meticulously scan the cosmic sky for any indication of artificial signals. The underlying principle is elegantly straightforward. If another civilization endeavors to communicate across interstellar distances, radio waves represent a highly efficient medium for such a transmission. They travel at the speed of light, are unimpeded by intervening dust and gas clouds, and certain frequencies, such as the one emitted by neutral hydrogen at 1.42 gigahertz, are considered universal beacons that any technologically advanced species would likely recognize. For decades, SETI has maintained its vigil, and for decades, the universe has responded with an unbroken silence. It is true that potential candidates have emerged, brief signals that initially sparked considerable interest. The WOW signal in 1977 and the BLC-1 signal in 2020 are notable examples. Each instance was met with a surge of excitement, only to be followed by disappointment when the signal failed to repeat, or was ultimately attributed to a terrestrial origin. The profound nature of this silence has prompted some scientists to question whether our current methods of searching are indeed the most effective. Perhaps radio waves are not the preferred communication channel for advanced civilizations. They might employ lasers, neutrinos, or even methods currently beyond our conceptual grasp. Alternatively, it is possible that they are not actively seeking to communicate with us at all. This leads us to the concept of technosignatures. Instead of actively listening for deliberate transmissions, we are now searching for indirect evidence of technology. This includes colossal structures capable of obscuring starlight, signs of industrial pollution within the atmospheres of exoplanets, the waste heat generated from energy consumption, and, pertinent to our current discussion, the presence of interstellar probes, objects that traverse the vast distances between stars, equipped with instruments, power sources, and potentially communication apparatus. Could Comet 32 Atlas, in fact, be such an object? Let us meticulously examine the prerequisites for such a hypothesis. Firstly, a viable power source is essential. While solar panels are effective in the vicinity of a star, they would be rendered useless in the vast emptiness of interstellar space. Nuclear power presents a viable alternative. A single kilogram of enriched uranium, for instance, can yield approximately 24 million kilowatt-hours of energy, sufficient to power a modest spacecraft for many years. Another option includes radioisotope thermoelectric generators, devices similar to those utilized on the Voyager and Cassini missions, which are capable of providing a steady supply of power for decades. Secondly, a communication system capable of transmitting across interstellar distances is imperative. This necessitates either a substantial power output, a large antenna, or a combination of both. The power requirements escalate with the square of the distance. At one point, 6 astronomical units from Earth, the distance through Atlas is projected to be on December 15th. This equates to approximately 240 million kilometers. To transmit a signal detectable over such a vast expanse with a mere 1-meter antenna, approximately 10 watts of transmitter power would be required. If one employs a highly focused beam and a sensitive receiver, this is an achievable engineering feat. A standard laptop computer, for example, consumes more power than this. However, a critical paradox emerges. Why would an interstellar probe deliberately wait until it is aligned with Earth to transmit its signal? If it has been journeying for potentially millions of years, why would the precise geometric alignment matter? One plausible explanation lies in the optimization of efficiency. If the probe possesses a limited power supply and aims to maximize the probability of detection, it would logically choose to transmit when it is in close proximity to the target star and situated in a favorable geometric configuration. Transmitting during such an alignment drastically reduces the required power and significantly enhances the signal-to-noise ratio. This is akin to waiting for a clear line of sight. Another possible rationale is a pre-programmed triggering mechanism. The probe might be designed to activate upon detecting specific environmental conditions, such as the presence of a technologically advanced civilization, the detection of radio emissions emanating from the target planet, or simply a favorable geometric alignment that signals the opportune moment to announce its arrival. Naturally, all of this remains speculative. We currently possess no definitive evidence to suggest that 33 Atlas is anything other than a comet. However, this speculation is firmly rooted in plausible engineering principles. What might a signal originating from 33 Atlas actually sound like? The nature of such a signal would depend entirely on the sender's intent. A rudimentary beacon might consist of a repetitive pulse transmitted at a specific frequency, modulated in a manner that unequivocally identifies it as artificial. Examples could include sequences of prime numbers, fundamental mathematical constants, or a patterned sequence that could not possibly arise from natural cosmic processes. A more complex message might encode intricate information, such as images, textual data, or descriptive information about the sender. The fundamental challenge lies in rendering such a message comprehensible to a recipient who may not share a common language or even a shared understanding of mathematics. SETI researchers have grappled with this very problem for decades. The prevailing consensus is that any civilization possessing the technological prowess to construct an interstellar probe would also possess the intelligence to design its signal in a manner that is unmistakably artificial. Such signals would likely incorporate redundancy, error correction codes, and utilize universal concepts that transcend cultural boundaries. If we were to receive such a signal from 33 Atlas on December 15th, its artificial nature would be immediately apparent. The pattern would be utterly unmistakable. However, a deeply unsettling consideration arises. What if the signal is not intended for us? What if 33 Atlas is merely a relay station, transmitting messages between distant nodes within a galactic network? In such a scenario, we would essentially be eavesdropping on a conversation in which we are not participants. The signal might not be designed for straightforward interpretation. It could be encrypted or compressed in ways that render it indistinguishable from random noise to our current analytical capabilities. We might detect the carrier wave, clear evidence of a transmission, but remain entirely oblivious to its content. This hypothetical situation is simultaneously exhilarating and profoundly frustrating. It would serve as irrefutable proof that we are not alone in the universe, and would validate the existence of interstellar communication and its ongoing practice. Yet it would also leave us feeling like mere outsiders, akin to primitives observing a discourse among adults without being invited to participate. Is that preferable or less desirable than the absence of sound? Frankly, I have no definitive answer. There remains another aspect to consider. What if the object known as 3I Atlas is not actively broadcasting, but rather acting as a reflector? Envision a civilization situated at an immense distance, desiring to establish contact with us, yet unwilling to endure a 50,000-year wait for a signal's reciprocal journey. They could utilize an interstellar body as a kind of mirror. A transmission is sent towards it, precisely timed to arrive when the celestial object is in alignment with Earth. This object would then redirect the signal, enabling our reception. The primary benefit of this method is speed. The journey of light from its origin to the reflective object might span years, but once it bounces, it reaches us in mere minutes. The overall duration for communication is significantly reduced compared to a direct transmission. For this strategy to be viable, the reflective body would need to possess a high degree of reflectivity at the necessary frequencies and be oriented correctly. These are substantial prerequisites. However, for a civilization possessing the capabilities for interstellar engineering, this might be achievable. Perhaps they strategically position reflective objects throughout their galaxy, enabling communication with nascent civilizations as they develop radio astronomy. December 15th could represent one such opportunity for communication. A specific moment when Earth, the celestial object 3I Atlas, and a distant transmitter converge in precise alignment. I wish to be unequivocal. I do not subscribe to the notion that 3I Atlas is an extraterrestrial reconnaissance vessel. I do not anticipate it transmitting on December 15th. The substantiating evidence for such extraordinary assertions is entirely absent. Nevertheless, this hypothetical scenario elucidates a crucial point regarding our methodology for detecting intelligence within the cosmos. We are not merely passively listening for a greeting. We are actively observing for anything that deviates from established patterns. Anything that implies deliberation, design, or intent. And when an interstellar object exhibits unusual behavior, even if that behavior has a perfectly natural explanation, our minds naturally gravitate towards the possibility that we are witnessing the indications of another consciousness. This inclination, this blend of anticipation and apprehension, is fundamentally human. It is the driving force behind SETI's continued efforts, despite decades of silence. And it is what imbues December 15th with a sense of importance, even in the absence of concrete justification. Part 10. The apparatus that acquires the ability to perceive the unusual. There exists an astronomical survey that commenced its operations in the year 2023, known as the Vera C. Rubin Observatory. Once it is fully operational, it will capture images of the entire observable sky every few nights, thereby generating a time-lapse chronicle of the universe. Every supernova, every asteroid, every star exhibiting variability, every transient astronomical event will be documented. The sheer volume of data is immense, amounting to 15 terabytes each night. Over the span of its 10-year operational period, it is projected to generate approximately 500 petabytes of imagery. It would be utterly impossible for any human to examine all of this data. Even a collective of thousands of astronomers working tirelessly around the clock would be unable to process it. Consequently, we are currently training artificial intelligence systems to undertake this task on our behalf. These systems, encompassing machine learning algorithms, neural networks, and artificial intelligence constructs, are capable of identifying patterns within astronomical images with a speed and accuracy surpassing that of any human observer. These sophisticated systems are already being employed in conjunction with existing surveys. They are instrumental in flagging supernovae, detecting asteroids, categorizing galaxies, and their proficiency is progressively improving each year. One of the particularly noteworthy capabilities of these artificial intelligence systems is their capacity for anomaly detection. The underlying principle is straightforward. The algorithm is initially trained using examples of conventional celestial objects. These include stars, galaxies, and comets that exhibit behavior consistent with established physical laws. Subsequently, this trained algorithm is deployed to analyze new data, tasked with identifying any element that does not conform to the established pattern, anything anomalous or irregular. The algorithm is not required to comprehend the precise nature of the anomaly or the underlying cause of its occurrence. Its sole function is to recognize when an entity deviates from the norm, when it is dissimilar to other observed phenomena. This methodological approach has already yielded significant discoveries, including the identification of unusual stellar variability, galaxies possessing peculiar structures, and transient events that defy classification within any known category. This approach is especially valuable when examining objects like 3I Atlas, a comet exhibiting activity at considerable distances from the Sun, possessing extreme polarization characteristics, and potentially deviating from its predicted orbital path. These are precisely the kinds of attributes that an anomaly detection algorithm is designed to flag. Imagine an artificial intelligence system that has been trained on the light curves of thousands of comets. It learns to recognize the typical variations in brightness as a comet approaches and then recedes from the Sun. Following this training, it is presented with the light curve data for 3I Atlas, If this curve displays characteristics that are inconsistent with the training data, such as unexpected peaks, dips, or slopes, the algorithm will generate an alert. A human astronomer then scrutinizes this flagged instance to ascertain whether it represents a genuinely significant observation or merely an artifact of the data collection process. This process is actively occurring at present, not exclusively for 3I Atlas, but for the broader spectrum of solar system objects. It is fundamentally altering our methods of discovery and study. We are no longer constrained by the limitations of human attention span and inherent biases. The algorithms are indifferent to whether an object is well known or obscure. They do not experience tedium when processing the 10,000th light curve. Their function is solely to process data and identify outliers. In essence, they function as superior observational tools compared to humans. However, there is a reciprocal aspect to consider. Artificial intelligence systems are susceptible to deception. They can misinterpret instrumental artifacts as genuine signals. They may become overly specialized to their training data, thereby failing to identify truly novel phenomena that bear no resemblance to anything previously encountered. Furthermore, they operate as black boxes. When a neural network designates something as anomalous, it is not always capable of articulating the rationale behind its decision. It merely outputs a probability score. The human astronomer is then tasked with interpreting the implications of this score. Therefore, consider the following scenario. In late November of 2025, a machine learning system, while analyzing observational data of 3I Atlas, detects an anomaly. This might manifest as a sudden fluctuation in brightness that deviates from the standard models of cometary activity. Alternatively, it could be a subtle alteration in the tail's orientation, suggesting a shift in the direction of material expulsion. Another possibility is a minute positional discrepancy that becomes apparent over multiple nights of observation. The algorithm flags this deviation. Subsequently, this flag is reviewed by a human operator, who must then make a crucial determination. Is this phenomenon authentic or merely extraneous noise? If it is deemed to be authentic, what are the subsequent steps? Ideally, this would involve conducting follow-up observations, directing additional telescopes towards the object, acquiring higher resolution imagery, performing spectral analysis, and ultimately attempting to characterize the anomaly and ascertain its origin. However, astronomical observation resources are finite. It is not feasible to immediately suspend all other observational priorities to focus on a single object unless its significance is definitively established. Consequently, a judgment call must be made. How certain is the observer that the anomaly is genuine? How compelling would the discovery be if it were indeed authentic? And how much of their limited observational time are they willing to allocate to a potential but unconfirmed finding? This is where the date of December 15th becomes relevant. If the anomaly detection system flags something unusual concerning 3I Atlas in the weeks preceding the celestial alignment, that alert gains heightened importance. It is no longer merely an isolated anomaly. It becomes a potential precursor to an event, a catalyst, a culmination. This narrative imbues the observation with greater significance, making it more deserving of intensive follow-up, even in the face of scientific uncertainty. Now let us broaden this perspective beyond the specific case of 3I Atlas. We are entering an era where artificial intelligence systems will continuously monitor the heavens, identifying anomalies, and generating alerts. Some of these alerts will prove to be false positives, while others will represent genuine but commonplace discoveries. A very small fraction, however, will signify entirely novel phenomena that will fundamentally reshape our understanding of the universe. The inherent challenge lies in sifting through these alerts, discerning which ones warrant serious attention and which can be disregarded. In a sense, these advanced computational systems are extending our sensory capabilities. They are enabling us to perceive patterns and changes that would remain imperceptible to unaided human observation. Yet, they also introduce new forms of uncertainty. When a human astronomer makes a discovery, they can articulate precisely what they observed and provide a clear explanation for its significance. When an artificial intelligence system flags an anomaly, the output is often merely a numerical value, a confidence score. One must place trust in the algorithm's ability to perform a sensible analysis, even when its reasoning process cannot be fully scrutinized. December 15th serves as a crucial test case for this emerging paradigm. If multiple artificial intelligence systems, trained on disparate datasets and employing diverse architectural designs, all identify 3I Atlas as anomalous in the days leading up to the alignment, this would constitute a potent indicator. It would suggest that a genuine phenomenon is unfolding, something that transcends individual measurement errors or the peculiar idiosyncrasies of specific algorithms. Conversely, if the flagged anomalies are inconsistent, or if they dissipate upon careful re-examination of the data, this would imply that the anomalies were likely artifacts. In either scenario, we will gain valuable insights into the effective utilization of these tools, the delicate balance between algorithmic insights and human skepticism, and the navigation of a universe where discovery is increasingly mediated by complex algorithms that we do not fully comprehend. Part 11. The political considerations of planetary defense. In the year 2013, an asteroid measuring approximately 20 meters in diameter entered Earth's atmosphere above Chelyabinsk, Russia, and detonated with an explosive force equivalent to roughly 500 kilotons of TNT. The resulting shockwave shattered windows across 6 municipalities. Over 1,500 individuals sustained injuries, predominantly from flying glass fragments. The asteroid had gone undetected prior to its impact. We were afforded no warning, no opportunity for evacuation, and no means to deflect or neutralize it. The Chelyabinsk incident served as a stark wake-up call. It underscored Earth's vulnerability and the existing deficiencies in our detection systems. In response, space agencies globally augmented their programs dedicated to monitoring near-Earth objects. NASA established the Planetary Defense Coordination Office. The United Nations sanctioned the formation of the International Asteroid Warning Network, abbreviated as IAWN, and the Space Mission Planning Advisory Group, known as SMPAG. These organizations are responsible for coordinating observations, assessing potential threats, and formulating strategies for potential mitigation missions. Their mandate is to ensure that an event like Chelyabinsk does not recur, or if it does, that we are adequately forewarned. However, a fundamental tension exists at the core of planetary defense. How can risk be communicated to the public without inducing widespread panic? If an asteroid is detected with a 1% probability of impacting Earth within the next 10 years, should this information be disclosed immediately? Or should one await a more precise estimation of the probability? Should no information be disseminated and the matter be handled discreetly? There is no universal consensus on this matter. Different agencies adhere to distinct policies, and these policies are subject to continuous debate and revision. Enter 3I Atlas. It does not qualify as a near-Earth object in the technical sense. Its closest approach to Earth is 1.8 astronomical units, a distance significantly beyond the established threshold that defines a potentially hazardous asteroid. Nevertheless, it represents an interstellar visitor, and our experience with such entities is limited. The passage of Oumuamua, for instance, raised questions regarding the classification and dissemination of information pertaining to such objects. Should they be categorized alongside asteroids, comets, or as an entirely novel class of celestial body? Some observers have posited that 3I Atlas was briefly included on internal watch lists maintained by planetary defense organizations, not due to any direct impact threat it poses, but because its unusual behavior warrants more intensive observation. These watch lists are typically confidential. They are employed for training exercises, the development of protocols, and interagency coordination. Objects are added to and removed from these lists based on evolving risk assessments. The public is rarely informed about these listings unless a situation escalates to the point of issuing a formal warning. If 3I Atlas were indeed placed on such a list, what would that signify? Most likely nothing of dramatic consequence. It would simply indicate that an entity, somewhere within the relevant organizations, deemed the object's trajectory or characteristics to be sufficiently uncertain to warrant additional scrutiny. Perhaps the intention was to practice observation protocols. Perhaps it was an exercise in rapidly acquiring data and refining an orbital calculation. Or perhaps it was simply a measure of prudent caution. However, within the realm of conspiracy theories, inclusion on a watch list is often interpreted as evidence of a hidden danger, as proof that authorities possess knowledge they are deliberately withholding. Furthermore, there is the issue of disclosure protocols concerning potential technosignatures. The protocols established by the SETI community, following the detection of potential extraterrestrial signals, outline specific steps to be taken. Key principles include verification of the signal prior to public announcement and consultation with relevant stakeholders. However, these are merely guidelines, not legally binding regulations. There is no enforcement mechanism, and they were primarily formulated with radio signals in mind, rather than the ambiguous behavior of physical objects. If 3I Atlas were exhibiting characteristics suggestive of an artificial origin, who would bear the responsibility for deciding whether and when to make a public announcement? NASA, the European Space Agency, the International Astronomical Union, the United Nations? The answer remains unclear, and this ambiguity creates fertile ground for speculation. If no public announcement is made, is it because there is nothing to report? Or is it because the announcement is being deliberately delayed while experts deliberate on its implications? The broader context is critically important here. We are currently living in an era characterized by a pervasive distrust of established institutions, government agencies, scientific bodies, and media organizations alike face skepticism from significant segments of the populace. When these institutions assert that there is no cause for alarm, many individuals interpret this as a sign that something is being concealed. This dynamic is observable in the responses to pandemics, in the discourse surrounding climate science, and in the forecasting of space weather. and it is also evident in the discourse surrounding 3I Atlas. From a policy standpoint, the fundamental challenge lies in striking a balance between transparency and responsibility. Excessive transparency too early in the process can lead to misunderstanding and fear. Conversely, insufficient transparency, particularly when delayed, can erode public trust and foster the growth of conspiracy theories. The ideal scenario involves disseminating accurate and timely information using language that the general public can readily comprehend. However, achieving this ideal is inherently difficult when the scientific understanding itself is inherently uncertain and continually evolving. December 15th occupies a pivotal position at the confluence of these various tensions. It represents a specific date, a juncture at which an event may or may not transpire. If various agencies have been meticulously tracking anomalies in 3I Atlas's behavior, December 15th would naturally serve as a significant checkpoint, a moment to ascertain whether earlier predictions hold true or if something unexpected occurs. Should an event indeed manifest, even if it is minor and ultimately explainable, the pressure to disclose this information will be immense. Social media platforms will undoubtedly become inundated with discussions. Amateur observers will readily share their data. The narrative will propagate irrespective of official desires. Conversely, if nothing of consequence occurs, the ensuing silence will be interpreted in diverse ways. Skeptics will likely proclaim, "We told you so," dismissing the preceding speculation as unfounded. Proponents of the extraordinary claims will suggest that the event was deliberately concealed or that its true effects are being suppressed. The agencies themselves will likely remain silent, preferring to allow the non-event to fade from public consciousness without comment. What I find particularly compelling is how this situation illuminates the limitations of our current governance structures when confronted with cosmic phenomena. We possess established protocols for known threats, such as asteroids. We have procedures in place for potential signals from extraterrestrial sources. However, we lack comprehensive protocols for ambiguous situations where an object exhibits unusual behavior without posing a direct threat. Situations where scientific understanding remains provisional, yet public interest is exceptionally high, and the distinction between a natural phenomenon and an artificial object is indistinct. December 15th may compel us to develop such protocols, or it may simply be relegated to another footnote in the lengthy history of cosmic alarms that ultimately proved to be unfounded. In either case, it presents a valuable learning opportunity. Part 12. When the Sun exhibits erratic behavior, the Sun is not a placid and predictable star. It is a turbulent sphere of plasma, permeated by magnetic fields that twist and snap with the intensity of overstretched rubber bands. Periodically, these magnetic fields release their stored energy in violent occurrences known as solar flares and coronal mass ejections. These explosive events propel billions of tons of charged particles into space at velocities ranging from several hundred to over 1,000 kilometers per second. Upon reaching Earth, these particles interact with our planet's magnetic field, precipitating geomagnetic storms. While these storms are typically minor, producing stunning auroras and perhaps causing some radio interference, they can occasionally be severe. In 1859, the Carrington event, the most significant geomagnetic storm ever recorded, generated auroras visible as far south as the Caribbean and ignited telegraph systems. A storm of comparable magnitude occurring today could inflict damage on satellites, disrupt GPS functionality, and cause widespread power grid failures across entire continents. The primary challenge lies in prediction. We can observe coronal mass ejections as they depart the Sun and estimate their arrival time at Earth, which usually occurs within a few hours. However, forecasting their precise impact is considerably more difficult. The intensity of a geomagnetic storm is contingent upon the orientation of the magnetic field embedded within the ejected plasma. If this field is aligned in opposition to Earth's magnetic field, it couples efficiently, resulting in a powerful storm. Conversely, if the fields are aligned in parallel, the coupling is weak, and the storm is comparatively mild. We are unable to measure the field's orientation until the plasma reaches satellites positioned between the Sun and Earth, approximately 1 hour before its potential impact. This provides a very limited window of warning. In 2025, the Sun is nearing the zenith of its 25th solar cycle. Activity levels are exceptionally high. Flares and coronal mass ejections are frequent occurrences. Space weather forecasters are engaged in issuing alerts and closely monitoring for significant events. And this is where the situation becomes particularly intriguing. What if, around December 15th, we were to experience an unanticipated geomagnetic storm? What if a coronal mass ejection were to arrive at Earth concurrently with the alignment of 3I Atlas? How would we differentiate between a disturbance of solar origin and a hypothetical effect caused by the comet? The answer is that we likely would not be able to do so, at least not immediately. Both scenarios would produce analogous signatures: heightened auroral activity, fluctuations in Earth's magnetic field, increased radiation levels detected by satellites, and disruptions to radio communications. The timing would certainly be suspect, but timing alone does not establish causality. Correlation does not imply causation. Even if a geomagnetic storm were to coincide precisely with the December 15th alignment, it could simply be a matter of chance. However, let us delve deeper. Solar storms possess a distinct structure. They exhibit characteristic rise times, peak intensities, and decay patterns that adhere to established physical principles. The attributes of a storm are intrinsically linked to the velocity and magnetic configuration of the coronal mass ejection that initiated it. Space weather scientists can frequently trace the origin of a storm back to its solar source, identifying the specific flare or eruption responsible. If a storm were to arrive on December 15th and we could definitively ascertain its solar origin, this would resolve the matter unequivocally. It would be a solar event, not a cometary one. Nevertheless, what if the characteristics of the storm did not precisely align with the identified solar event? What if its intensity exceeded expectations, or if the magnetic field orientation was unusual, or if there were secondary peaks that deviated from the standard profile? In such instances, we would enter a zone of ambiguity. It is possible that our solar wind models are incomplete. It is conceivable that the plasma experienced additional acceleration during its transit. Or perhaps, just perhaps, there was a contributing factor from an alternative source. I wish to walk you through a hypothetical scenario. While speculative, it is grounded in physical principles. Let us assume that the ion tail of 3I Atlas contains magnetic structures, specifically flux ropes, which are formed by the interaction between the comet's outflowing plasma and the interplanetary magnetic field. These structures are propagating outward from the comet at the speed of the solar wind, approximately 400 kilometers per second. On December 15th, Earth would be situated downstream of the comet at a distance of roughly 1.6 astronomical units, equivalent to 240 million kilometers. At a velocity of 400 kilometers per second, material ejected from the comet would require approximately 7 days to reach Earth. Now suppose that around December 8th, a week prior to the alignment, the comet experienced a sudden surge in activity, an outgassing burst, a fragmentation event, or some other phenomenon that released a substantial volume of ionized material into its tail. This material would become entrained within the solar wind and carried towards Earth. By December 15th, at the precise moment of the celestial alignment, this enhanced plasma would reach Earth's magnetosphere. Concurrently, the Sun would happen to release a coronal mass ejection. While not directly aimed at Earth, it would be sufficiently close that its peripheral edges would interact with our magnetosphere. The combined effects of the solar and cometary events would arrive simultaneously, leading to a geomagnetic disturbance that is either more potent or more intricate than what the solar contribution alone would produce. Would we be able to detect the cometary contribution? It is a possibility. If we had spacecraft positioned to monitor the solar wind upstream of Earth, they might detect anomalies in its composition. The comet's celestial vapor might display distinct proportions of elements and their isotopic forms when contrasted with the Sun's plasma. It's conceivable it would exhibit elevated levels of carbon or nitrogen. Furthermore, it could reveal spectroscopic markers characteristic of cometary molecules. Should instruments be calibrated to detect these specific signatures, they might indeed be observed. However, herein lies the predicament. Our current observational capabilities are not oriented toward such a pursuit. The probes deployed within the solar wind are engineered to monitor solar emanations, not the contributions from comets. They meticulously record bulk plasma attributes such as density, velocity, and magnetic field strength, but do not routinely perform detailed compositional analysis. Consequently, any cometary signature, if present, could easily go unnoticed. The ensuing space disturbance would be unequivocally attributed to a solar event, and December the 15th would pass without anyone realizing that 3 Atlas had made a modest yet discernible contribution to Earth's space environment. This is the frustrating aspect of ambiguous occurrences. Even when they transpire and produce tangible effects, they can be obscured by other phenomena or overlooked entirely because our detection apparatus is not configured to identify them. Science is not an infallible arbiter. We perceive what our instruments are designed to measure, and we interpret these observations through the framework of our existing models and preconceived notions. Any effect that falls outside this established paradigm risks remaining imperceptible. An additional consideration warrants attention: the possibility of false alarms. The forecasting of space weather is an imprecise discipline. Occasionally, forecasters predict a significant solar storm only for nothing substantial to materialize. This might occur if a coronal mass ejection misses Earth, if its magnetic field orientation proves unfavorable, or if it dissipates during its transit. Conversely, a solar storm might arrive with minimal forewarning if the eruption originated on the far side of the Sun and only became apparent as it traversed into Earth's field of view. If forecasters anticipate heightened geomagnetic activity for December the 15th, and it fails to materialize, What conclusions can be drawn? It could simply signify an inaccurate prediction. Alternatively, it might point to an altogether different explanation. Perhaps the predicted solar storm was indeed real, but its impact was neutralized or deflected by plasma emanating from 3I Atlas. It's plausible that the celestial alignment created a shielding effect, thereby mitigating the storm's intensity. While this scenario is highly speculative, it effectively illustrates the inherent difficulty in interpreting null results. The absence of an anticipated effect can be as enigmatic as the presence of an unexpected one. My central argument is this: December the 15th is situated within a space weather milieu that is inherently intricate and unpredictable. The Sun is in a highly active phase, with coronal mass ejections occurring frequently. Earth's magnetosphere is perpetually subjected to the buffeting of a variable solar wind. Against this backdrop of pervasive noise, discerning a subtle contribution from an interstellar comet would present an exceptionally formidable challenge. It is akin to attempting to discern a whisper amidst the clamor of a crowded assembly. Even if the whisper is present and conveys something significant, it might still be missed. This does not imply we should cease our efforts. The networks dedicated to monitoring space weather are more sophisticated than ever before. We possess an array of satellites, ground-based magnetometers, radar systems, and auroral cameras, all contributing data to real-time analysis platforms. Should anything out of the ordinary occur on December the 15th, it will undoubtedly be recorded. The pertinent question is whether this anomaly will be recognized at the time of its occurrence, or if it will only surface later, when researchers meticulously sift through archival data in search of irregularities. This leads to a rather sobering reflection. How many peculiar events have already transpired that have escaped our notice? On how many occasions has the universe attempted to communicate with us, only for us to remain oblivious? We tend to discover only that which we actively seek, and we direct our search towards areas where we anticipate finding something. Everything else invariably slips through the cracks. December the 15th might represent one such oversight, or it could herald a moment when our attention is finally drawn. Part 13 delves into fast radio bursts and the enigma of cosmic static. In the year 2007, astronomers examining archived data from the Parkes radio telescope in Australia made a remarkable discovery, something that defied conventional understanding. They identified a pulse of radio waves, lasting a mere few milliseconds, yet possessing an energy output equivalent to the Sun's entire daily emission. This pulse exhibited a distinctive dispersion pattern, wherein different frequencies arrived at slightly staggered intervals, indicating its passage through extensive volumes of ionized gas. The conclusion was unavoidable. This signal had originated from far beyond the confines of our galaxy, from a distance spanning billions of light years. It was designated as a fast radio burst, or FRB. Initially, it was considered an anomaly, a singular detection that could potentially be an instrumental artifact or terrestrial interference. However, subsequent investigations revealed more such events. Dozens, then hundreds, were identified. Some of these bursts repeated, while the majority did not. Their origins remained shrouded in mystery. Magnetars, ultra-dense neutron stars characterized by formidable magnetic fields, emerged as a leading candidate. The collision of black holes presented another plausible explanation. Predictably, some theories posited an artificial origin, suggesting signals from extraterrestrial civilizations or pulses from interstellar communication networks, thereby hinting at our non-singular existence in the universe. The hypothesis of an artificial source is largely regarded as a fringe theory by the majority of astronomers, with naturalistic explanations deemed sufficient to account for the observed characteristics. However, the fundamental issue remains. We do not possess definitive knowledge regarding their cause. Every proposed naturalistic model encounters significant challenges, and each attempt to explain the diverse observed properties necessitates either exceptional circumstances or precise fine-tuning. The enigma persists, and such mysteries invariably fuel speculation. Fast forward to the year 2025. The detection of FRBs has become routine. Observatories across the globe are equipped with specialized instruments for their identification and characterization. The catalog now encompasses thousands of recorded events. Certain among these events exhibit genuinely peculiar traits. Repeating bursts with discernible periodicity, suggesting an origin from a rotating celestial body. Bursts displaying intricate subpulse structures hinting at multiple emission sites, and bursts that cluster in time, appearing in sequences separated by prolonged periods of silence. Now envision this. On December the 15th, 2025, precisely as 3I Atlas approaches its alignment with Earth, radio telescopes register a fast radio burst. The timing, one might initially assume, is purely coincidental, given the constant occurrence of FRBs worldwide. Consequently, detecting one on any given day would not be considered remarkable. This would remain the case unless the FRB possessed unusual attributes. For instance, if its dispersion measure, a parameter indicating its travel distance, implied an origin inconsistent with a distant extragalactic source, or if its arrival direction, when triangulated by multiple observatories, pointed uncomfortably close to the celestial coordinates of 3I Atlas. Such a confluence of factors would be considerably more challenging to dismiss as mere chance. The probability of a random FRB originating from the vicinity of 3I Atlas at the exact moment of alignment would be exceedingly small, though not zero, yet sufficiently low to warrant serious attention. Furthermore, if the FRB exhibited additional peculiar characteristics, such as a repeating pattern suggestive of intelligent design, the eyebrows would undoubtedly rise even higher. Let me clarify the statistical probabilities involved. The celestial sphere encompasses approximately 41,000 square degrees. If FRBs are distributed uniformly across the sky at a rate of a few per day, the likelihood of detecting one from any specific square degree region on any given day approximates 1 in 10,000. 3I Atlas occupies an infinitesimally small fraction of a square degree. Therefore, the prior probability of such a coincidence is genuinely minuscule. Should it occur, it would necessitate a thorough explanation. However, the situation becomes more complex. FRB detection is not uniformly distributed across the sky. Observatories often have preferred pointing directions dictated by their observation schedules. Furthermore, on December the 15th, if both amateur and professional astronomers are intently observing 3I Atlas due to the heightened anticipation surrounding its alignment, radio telescopes might also be directed towards that specific celestial sector. This would not necessarily be for the explicit purpose of searching for FRBs, but rather to investigate potential radio emissions originating from the comet itself. Consequently, if one is observing a particular patch of the sky, The probability of detecting an FRB from that region increases simply because it is under observation. This inherent selection bias complicates any definitive interpretation. Was the detected FRB genuinely associated with 3I Atlas, or did we merely intercept a random FRB due to our focused observation of that area? Disentangling these competing possibilities demands meticulous statistical analysis and, ideally, data from multiple observatories that were not exclusively focused on the comet. An alternative scenario merits consideration. Suppose 3I Atlas itself were to emit a radio pulse. This would not qualify as a fast radio burst in the technical sense, as those are extragalactic in origin. Instead, it would constitute a transient radio signal, a burst of electromagnetic radiation triggered by an event within the comet's coma or tail. Plasma instabilities are known to generate radio waves. Lightning discharges within dusty cometary environments have been proposed as a potential mechanism, though they have not been definitively observed. If such a discharge were to occur within 3I Atlas during its alignment, it might produce a detectable radio signal. This signal would be considerably weaker than an FRB, given its proximate origin, rather than originating from billions of light-years away. However, at a distance of 1.6 astronomical units, a moderately powerful emission could still be detected by sensitive radio telescopes. Such a signal would possess different characteristics compared to an FRB. Little to no dispersion, as the radio waves would not have traversed intergalactic space. A broader frequency range rather than being narrowly focused, and potentially a longer duration. If radio astronomers were to detect such a signal on December the 15th, it would represent a genuine scientific breakthrough, providing evidence of a novel form of cometary activity, a mechanism for electromagnetic emission not currently accounted for in existing models. The scientific publications detailing such a discovery would undoubtedly be fascinating, yet it would not constitute evidence of intelligence or an artificial origin. It would simply reveal a facet of physics that comets were previously not known to exhibit. The fundamental challenge lies in the fact that detecting radio emission from comets necessitates precise knowledge of where and when to direct observation. The majority of radio telescopes are dedicated to observing distant celestial objects such as galaxies and quasars or pulsars. Directing them towards a comet is an unconventional practice, typically requiring a specific request, and telescope time is a precious resource. Therefore, unless a compelling justification exists for observing 3I Atlas at radio wavelengths on December the 15th, the observation would likely not occur. However, this is precisely where speculative discourse could prove beneficial. If a sufficient number of astronomers engage in discussions about December the 15th, and if the alignment date gains widespread recognition within the scientific community, an individual might be motivated to point a radio telescope at the comet simply to explore the possibilities. This is the kind of initiative a graduate student might undertake, utilizing a few hours of observing time on a smaller instrument to investigate potential radio emissions, either to confirm or refute their existence, or to uncover something entirely novel. The risk is minimal, while the potential reward could be substantial. Thus, an intriguing feedback loop emerges. Speculation stimulates observation, which in turn generates data that either validates or contradicts the initial speculation. In the most favorable outcome, we acquire new knowledge about comets. In the least favorable scenario, we accumulate additional data that enhances our understanding, even if it pertains to null results. In either case, the speculative discourse possesses intrinsic value by motivating concrete scientific inquiry. Perhaps this is the true significance of December the 15th. Not that anything extraordinary will transpire, but rather that individuals are paying attention, and that an otherwise routine astronomical event has captured sufficient imagination to warrant serious investigation. The universe teems with wonders that remain unobserved due to a lack of attentive scrutiny. On this occasion, at least, people are looking. Part 14 addresses the pivotal question that redefines our perspective. Allow me to guide you back to fundamental principles, to the underlying question that fuels all this conjecture, analysis, and anticipation. The question is not what 3i Atlas will do to Earth. The question is whether we are alone. Every quest for anomalies, every contemplation of artificial origins, every hope that December the 15th might yield something unforeseen, all trace their roots back to that profound inquiry. We have been posing it for as long as we have gazed upon the celestial expanse. Ancient philosophers pondered the existence of other worlds beyond our own. Medieval scholars debated whether the divine would deign to create life elsewhere in the cosmos. In the 20th century, scientists constructed radio telescopes to listen for extraterrestrial signals. And now, in the year 2025, we observe an interstellar visitor, contemplating whether it carries a message. Statistical probabilities suggest that we should not be alone. Our galaxy harbors an estimated 100 to 400 billion stars. Recent exoplanet surveys indicate that the majority of stars are orbited by planets. Potentially habitable worlds, planets situated within the temperature zone conducive to liquid water, number in the billions, solely within the Milky Way galaxy. The universe has had 13.8 billion years to foster the development of life, intelligence, and technology. The requisite raw materials are abundant, and the temporal span is sufficient. So, where is everyone? This is the Fermi paradox, named after physicist Enrico Fermi, who articulated it during a casual lunch discussion in 1950. If intelligent life is prevalent, we should observe evidence of its existence. Megastructures, radio signals, probes traversing our solar system. The absence of such evidence, the profound silence, represents one of the most significant enigmas in science. Perhaps life is exceedingly rare, perhaps intelligence is even rarer. It's conceivable that civilizations self-destruct before achieving interstellar capabilities. They might exist, but remain concealed. Or they could be present, yet unrecognized by us. 3 Atlas serves as a test case for one interpretation of this latter hypothesis. If advanced civilizations employ interstellar objects as vessels for probes or communication devices, then every object that enters our solar system from interstellar space warrants potential significance. We cannot dismiss any of them without rigorous examination. Oumuamua taught us that its peculiar acceleration, its unconventional shape, and its lack of outgassing remain inadequately explained features. Mainstream scientific consensus leans towards naturalistic explanations involving hydrogen ice or exotic cometary compositions. However, a segment of researchers, including respected astronomers, maintain that an artificial origin remains a plausible hypothesis. With 3i Atlas, we have a second opportunity, a second chance to apply everything we learned from Oumuamua. This time, we possess superior instruments, a greater number of observers, and earlier detection capabilities. If there is anything artificial about this object, our prospects of discovering it are enhanced compared to our experience with Oumuamua. The alignment geometry on December the 15th presents a natural experiment, a moment at which any deliberately timed signal or effect would manifest. However, I wish to shift the perspective momentarily. Suppose our current assumptions are incorrect. Suppose there is nothing artificial about 3I Atlas. Suppose December the 15th arrives and departs without any anomalies, signals, or unexpected phenomena. What implications does this hold? Does it signify our solitude? Certainly not. It merely indicates that one interstellar comet out of 3 detected objects was not artificial. This hardly constitutes a comprehensive survey. The pursuit of extraterrestrial intelligence is a protracted endeavor. It may span centuries or even millennia. Alternatively, it could transpire tomorrow, when a radio telescope captures an unmistakable signal, when a probe reveals its presence, or when an event occurs that leaves no room for doubt. We are uncertain of the timescale or the probabilities involved. We only know that if we cease our search, we guarantee that we will never find anything. December the 15th holds significance, not because it is likely to yield a dramatic revelation, but because it represents a specific, testable moment. We can direct our instruments, gather data, and subsequently analyze and interpret it. If an event occurs, we document it. If nothing occurs, we document that as well. Either outcome contributes to our accumulated knowledge. Either outcome narrows the spectrum of possibilities. There is a profound aspect to standing on a planet hurtling through space, observing an object originating from another star system as it passes nearby, and contemplating whether it might be carrying a message from beings unknown to us. It embodies an act of optimism, of hope, and of extending our reach beyond the confines of our experience towards something greater. Even if the answer proves to be negative, even if we are merely conversing with ourselves in an empty chamber, the very act of inquiry alters us. It serves as a reminder that we are an integral part of something far larger than our individual lives or even our entire civilization. The astronomer Carl Sagan aptly stated that the cosmos resides within us, that we are composed of stardust contemplating the stars. He was correct, but the connection runs deeper than mere chemistry. We represent a means by which the universe can comprehend itself. And if other intelligences exist, other minds grappling with similar questions, gazing at the same stars, then we are intrinsically linked to them through this shared curiosity, through the simple act of wonderment. 3I Atlas is, most likely, almost certainly composed of rock and ice. However, even if it is merely a comet, it is a comet that originated elsewhere. It carries information pertaining to a different region of the galaxy, concerning the composition of interstellar clouds, the formation of planetary systems, and the processes that shape matter across vast expanses of space and time. That information is inherently valuable. That narrative is worthy of being heard. And if, against all expectations, against all reasonable conjecture, it proves to be more than just rock and ice, if December the 15th ushers in something unforeseen, then everything will change. Not merely our scientific understanding or technological capabilities, but our perception of our cosmic position, our definition of ourselves, and our potential future trajectories. This is what is genuinely at stake. Not our physical security, as Earth will remain unharmed irrespective of 3I Atlas's actions or inactions. Rather, it is our cosmic solitude, our philosophical isolation, the fundamental question of whether we are the universe's sole attempt at self-awareness, or merely one entity among many. December the 15th will not provide a definitive answer to this question, but it may offer a clue, a hint, a direction for further investigation. And at times that is sufficient. Part 15 describes the vigil. And so here we are. The days leading up to December the 15th, 2025, are upon us. Across the globe, telescopes are meticulously trained on a specific sector of the sky, where 3I Atlas navigates its hyperbolic trajectory. Amateur astronomers are diligently preparing their equipment, calibrating their cameras, and finalizing their observation schedules. Professional observatories are conducting routine surveys that will incidentally capture the comet alongside thousands of other celestial objects. Space weather forecasters are continuously monitoring the sun for signs of coronal mass ejections. Radio astronomers are meticulously scanning the cosmos for fast radio bursts and any anomalous signals. The majority of these individuals anticipate nothing out of the ordinary. They are engaged in the practice of science, accumulating data, and adhering to established protocols. December the 15th is simply another date on the calendar, another night dedicated to astronomical observation. However, a subset of them harbor a sense of anticipation. Some are observing with a heightened degree of attentiveness, fueled by a touch more hope, apprehension, or sheer curiosity. They are contemplating whether this might be the night when something fundamentally changes. Allow me to outline what to observe if you wish to follow these developments. Firstly, space weather. The National Oceanic and Atmospheric Administration operates a Space Weather Prediction Center, which furnishes real-time data on solar activity and geomagnetic conditions. Their website provides current aurora forecasts, solar wind parameters, and geomagnetic indices. Should Earth's magnetosphere experience unusual disturbances on December the 15th, these data streams will reflect these events within hours. Look for abrupt increases in the K-index, a measure of geomagnetic activity. Observe reports of auroras appearing at latitudes where they are not typically visible. Monitor satellite operators for reports of anomalies or communication disruptions. Secondly, positional data. The Jet Propulsion Laboratory's Horizon system provides ephemeris predictions for 3I Atlas, accessible online. If you possess observational capabilities, either independently or through shared data from others, you can compare measured positions with predicted positions. Any consistent deviation exceeding a few arc minutes, corroborated by multiple independent observers, would be deemed significant. Online forums such as the Minor Planet mailing list and amateur astronomy communities on Reddit serve as platforms where such observations are frequently disseminated and discussed. Thirdly, photometry. Light curves illustrating the brightness variations of 3I Atlas over time are being meticulously compiled by amateur observers. If the comet exhibits unexpected brightening, dimming, or fluctuations on December the 15th, these phenomena will be evident in the photometric data. The challenge lies in differentiating genuine variations from measurement noise and atmospheric distortions. Multiple independent observations exhibiting similar patterns provide stronger validation than isolated reports. Fourth, we have radio-based investigations. This aspect presents a greater challenge for casual observers, as real-time data from radio telescopes is seldom accessible to the public. Nevertheless, organizations dedicated to SETI search for extraterrestrial intelligence, and certain university radio observatories occasionally issue updates regarding their findings. Should a significant and transient radio signal be detected originating from the direction of Object 3 Atlas, it is highly probable that an announcement will be disseminated within a matter of days through channels like astronomers' telegrams or comparable communication platforms. Fifth, consider the role of social media and news outlets. If a truly extraordinary event transpires, word of it will undoubtedly spread with remarkable speed. Scientists will share their thoughts on Twitter, online discussions will erupt, and media organizations will seize upon the story. The crucial difficulty lies in discerning genuine information from the surrounding noise within this deluge of data. Numerous claims will likely be exaggerated or misunderstood, and some will undoubtedly be entirely fabricated. Therefore, the application of critical thinking and diligent verification of sources becomes absolutely essential. Now let us consider the plausible outcomes. The most probable scenario is that the 15th of December will pass without any remarkable events. Object 3. Atlas will continue on its predetermined path, its luminosity diminishing as anticipated. No radio signals will be detected. The conditions of space weather will remain within their normal parameters. Amateur sky watchers will observe nothing out of the ordinary. And over the subsequent weeks, interest will gradually wane. The speculation will fade into obscurity, and 3 Atlas will be relegated to a mere footnote in history. It will become just another interstellar visitor that passed through without causing any significant disruption. This would be considered a null result. While it may be disappointing to those who were hoping for something extraordinary, it holds significant scientific value nonetheless. Null results serve to validate our existing models, confirming our understanding of comets to a degree that allows us to accurately predict their behavior. They indicate that interstellar objects, at least those we have detected thus far, are natural phenomena that do not necessitate exotic explanations. The second potential scenario involves minor deviations. These would manifest as small discrepancies from the predicted trajectory, perhaps a brief geomagnetic disturbance that may or may not be linked to the alignment, or an unexplained brightening event lasting only a few hours. Amateur position measurements might show slight offsets, barely discernible above the background noise. Such ambiguous signals would undoubtedly spark discussion, but would not lead to a revolutionary shift in understanding. Scientists would engage in debates regarding interpretations, with some positing that the anomalies are real and noteworthy, while others might attribute them to instrumental artifacts or mere coincidences. Scholarly papers would be published, and sessions at conferences would be dedicated to these findings, yet a definitive consensus would likely not emerge. The third scenario, that of a dramatic revelation, is the least likely, but possesses the greatest potential impact. This would involve a clear and unambiguous signal. Imagine a radio pulse that repeats with mathematical precision, a variation in brightness that encodes information, or a positional deviation so substantial that it could only be explained by the presence of propulsion. We might also observe satellite disruptions that perfectly correlate with the timing of the alignment and cannot be attributed to solar activity. In such a situation, we would possess genuine evidence that 3 Atlas is not entirely a natural phenomenon. the scientific community's response would be immediate and extensive, involving follow-up observations with every available instrument, emergency consultations among international space agencies, the activation of established post-detection protocols, and, inevitably, public disclosure. Such a groundbreaking discovery could not realistically be kept secret. Which of these scenarios will unfold? I do not possess this knowledge. No one does. This is precisely why the 15th of December holds significance. It represents a genuine unknown, a roll of the cosmic dice. Regardless of whether the outcome is ordinary or extraordinary, we will gain valuable insight. However, there is a crucial point I wish you to remember. The importance of December 15th extends beyond the events of that specific date. It symbolizes a moment when humanity across the globe unites in looking outward, observing an object originating from another star system, and posing questions about its true nature and origin. This shared focus, this collective curiosity, is a rare and precious phenomenon. On most days, the majority of people are occupied with their immediate concerns, local issues, and personal lives, which is perfectly understandable and indeed necessary. Yet on occasion we need to gaze upwards, to be reminded of our place within something vast, strange, and wonderful. 3 Atlas has provided us with a compelling reason to do so. Whether it is merely a comet or something more, it has connected us to the broader cosmos in a tangible manner. It has served as a reminder that space is not an empty void, that objects traverse the vast distances between stars, and that our solar system is an integral part of a dynamic galactic neighborhood. Furthermore, it has prompted us to contemplate whether we are alone in the universe, whether other beings are also observing their own skies and pondering the same fundamental questions. These profound questions will not be answered on December 15th. Their resolution will unfold over decades and centuries through persistent observation, rigorous analysis, and the occasional serendipitous discovery. December 15th represents but a single data point in this extended quest. Yet it is our data point, our moment, and our opportunity to observe and to wonder. Therefore, if you are able, observe. Follow the space weather reports, explore the astronomy forums, examine the incoming data, and ask yourself what you most hope to witness. Do you wish for confirmation that our understanding of the universe is complete, and that all events proceed according to natural laws? Or do you yearn for the surprise, the anomaly, the revelation that we are not alone, and that the cosmos is far more peculiar than we have imagined? In either case, December 15th is approaching. The countdown has already commenced. 3 Atlas is nearing its closest alignment. And somewhere out there, traversing the interstellar gulf, a visitor from another star system is poised for its most intimate encounter with Earth. Whether that encounter will be silent or profoundly communicative, we are on the verge of discovering.